Hi, my name is Kaylee Burt, and this is my lab report 5. This lab was Choose Your Own Adventure, and I decided to analyze the motion of a falling slinky. So purpose and findings. Purpose was to analyze the motion of a falling slinky to determine if the bottom stays motionless while the top is falling, and then compare the observed model to the predicted model. I tracked the top and bottom of the slinky using the program tracker and modeled the experiment using glow script code. And then a preview of the findings. Does the bottom stay stationary or immediately fall? The bottom of the slinky remains stationary until the top meets the bottom and the whole slinky falls to the ground. Can be explained by equal and opposite forces of gravity and tension on the bottom of the slinky. And then the observed model from tracker varies slightly to the predicted model, probably due to other forces on the slinky. Fundamental physics principles, we have the gravitational force. The slinky/tension force, like I said, is equal and opposite to the force of gravity. The drag force, the net force. And then Newton's second law / the momentum principle, we have the position update formula, velocity update formula, and the momentum principle. And then for initial conditions, system and surroundings, initial condition time is initially 0. I set the origin of the slinky to be the top of the slinky, so the original position of the bottom has a negative y coordinate, and then the initial velocity obviously 0 because it's at rest initially. And then the mass and the length of the compressed slinky I got from doing research of an average slinky size on the internet. So I got 0.22 kilograms for the mass and then 0.0571 meters for the compressed slinky. And then the proportionality constant, B, for the magnitude of drag force, I did through trial and error using closed script, which I got 0.99. And then the system is the slinky, the surroundings are the earth. Okay, so this is the video I uploaded to Tracker. I couldn't get the video to flip horizontally, so it's vertically, but I set the axis to the origin and made sure the coordinates are right, even though it's vertical. And then I used the calibration stick to set the scale of the compressed length to the compressed length of the slinky, which I mentioned earlier. And then that stick is right here. And then I used the track tool to track the change in position during each time interval. And then I tracked the top of the slinky and the bottom of the slinky. And then I used the results from Tracker as data points for the observed graph that we'll see later. Okay, so here's my glow script code. This code is modeled off of the code from Lab 2, and then the ball here is the slinky, so anytime it says ball, it's slinky. I changed the slinky's mass, initial position, initial velocity, t, delta t, and b to match the initial conditions already mentioned, and the ones in the Tracker video. And then here is the picture on the left is the code before the top half of the slinky hits the bottom, and it causes it to fall because this half accounts for the tension force that is equal and opposite to the force of gravity, which you can see here is Ft, and it doesn't account for the drag force. And then it uses the velocity update and position update formulas to track the motion, and then ended up printing the y position coordinates to use for the graph. And then this picture on the right doesn't account for the tension anymore and instead accounts for the drag force, which is here as Fd, and then also uses the velocity and position update formulas to track to update the position, and then prints the y position. Okay, so here's the graph of the y position points of the observed graph from Tracker and the predicted from GlowScript that I mentioned. Clearly the y position of the slinky doesn't change for the first more than half of the time because the gravitational force pulling the bottom of the slinky down is equal and opposite to the tension force pulling it up, like I said. So there's no motion on the bottom end until the top end hits it and it knows tension has changed and the whole slinky starts falling. Also, the predicted model drops faster than the observed graph, and it could be because there are other forces interacting with slinky in the video that aren't accounted for in the code and could be from other possible errors. And then this is the top versus bottom movement of the slinky. Both of the graphs are used from points from observed graphs in Tracker. As you see, the top falls normally with the force of gravity and then some other drag after the 0.95 seconds. And then you can see the point where the top meets the bottom and then it starts to fall together. Possible sources of error. The mass and assumed compressed length of the slink could be inaccurate because they were determined based on the average attributes of everyday slinkies from the internet. The video was in slow-mo, so it's hard to get the time frame and delta t right in Tracker. It was also very blurry, so the Tracker tool could have been a little inaccurate, human error. And then the drag force in the video could have not been simulated correctly using my code because B was calculated through trial and error. And then the computational model shows a steeper drop than in Tracker, and could be because tracking Tracker or the inaccuracy of the drag calculation. What does it mean? What if? So like, what if you add some sort of weight at the end of the slinky when you drop it? Will the bottom still remain stationary until the top meets it, or will the bottom fall immediately due to the weight? And the answer is, even with the weight on the bottom of the slinky still remains stationary until the top meets it and the whole slinky falls to the ground. So if like a golf ball was attached to the end of the spring, it would remain stationary because the tension force is equal and opposite to the force of gravity. Thank you.